Hello ladies and gentlemen, today we are going to start gas powered cycle, and again good morning, good afternoon, good evening to all of you. So gas power cycle, this is a very important invention in the world of thermodynamics. Gas power cycle, today's many engines depend upon the theory of these cycles. Gas power cycles, why we name it gas? As the name suggests, gas means air, power cycle means this is the working fuel of gas power cycle is air. Some of you confused that how air can be able to generate energy, because we use fuel in the cycles, in diesel cycles or the other cycles which is present nearby us in a realistic way. We are going to discuss about these in next upcoming values. Okay, so now it has been confirmed. Now okay, there is some okay, ideal cycles. These ideal cycles, why we call it ideal cycles? Because these not exist in reality. There are so many assumptions which we have to take to derive these equations, and the ideal cycles in which the internal combustion occur. Internal combustion means the combustion take place in a closed chamber, and there is also external combustion. In external combustion, as you apply your common sense, in which it means a combustion take place in not a closed chamber. Okay, so how can combustion take place in not a closed chamber? We will also discuss about it. Okay, so the internal combustion taking place cycles are Otto cycles, in which the spark ignition occur. It is a very important character of Otto cycle. Otto cycle, if I give you a brief view of Otto cycle, is developed by Nicholas Augusto Otto. It is also known as four-stroke engines. Otto cycle is, I already discussed it, it is used in internal combustion engines. There are four stroke cycle, consist of induction stroke, compression stroke, ignition or power stroke, exhaust stroke. If you remember the main parts of four stroke cycles, these are intake valve, in which we intake the mixture of air and fuel. If we take intake, then there must be a area of exhaust. So there is a exhaust valve, there is a piston, and if with piston, rings also come. So piston rings, and there is a combustion chamber must be there, and there is a connecting rod and a crankshaft to give the rotatory movements. And as the name suggests, it is a spark plug, a spark ignition, so there must be a spark plug. Okay, I'm not going in detail of Otto cycle, but if you want to know about Otto cycle, there is also my other tutorials in which you can get gather more knowledge about Otto cycle. I'm just not joking, I am serious about it. Okay, next one is diesel cycle. Diesel cycle is a combustion process of a reciprocating internal combustion engine. In it, fuel is ignited by the heat generated during the compression of the air in the combustion chamber. So the ignition is done by compressor, which is in contrast with Otto cycle, where the ignition is done by spark. Okay, Stirling and Ericsson cycles is now just become a hypothetical cycle, because the way of these cycles generates is not possible in realistic way. Brayton cycles is also known as gas turbine cycles, and Brayton cycles have a lot of use in modern days. Jet propulsion cycles, all Otto, diesel, Stirling, Brayton and jet propulsion cycles include internal combustion. And the ideal cycle in which the external combustion exists is the Rankine cycle. We are going to not talk about a lot about Rankine. Okay, there is a huge gap in ideal and actual. You know, ideal never exists in my way, and actual always exists. So if you take ideal cycle of PV diagram, then ideal it exists like this, and actual the process, if you draw the actual diagram of PV of a cycle, then the red mark represent the actual cycle. There are so many assumptions which we take in ideal cycles. The first assumption is cycle do not involve any friction, which is not possible. Second, to decrease the friction we use so many methods. Second is all expansion and compression process are quasi equilibrium process. quasi-equilibrium, it means reversible and very slow process. And third one is pipe connecting components have no heat loss, which is also not possible, but we take so many measures to decrease the heat loss, but it can't be zero. You know why? Neglecting changes in kinetic and potential energy. We neglected all the changes happened in kinetic and potential energy except in nozzles and diffusers. Okay, so we take a small look about Carnot cycle. Here the Carnot cycle start PV and TS diagram. PV pressure volume, TS temperature and entropy diagram. First, second, third, fourth. First to second, temperature is constant, heat is added in the cycle, and look the variation in P and V. There is not very steep variation in P and V, it is slightly sloped. Then second to third, it is isentropic process. Guess what is isentropic process? Isentropic process means at constant entropy. It means randomness of the system has not been disturbed. Second to third process, then third to fourth, again the heat is out. Whatever we take in, we have to out it, and it is at constant temperature. Then again 4 to 1, the compression exists because the volume decreases. Just take a line, straight line, 4 to 1, then you looked at the volume decreases, and 2 to third, then you looked at the volume increases. Then 2 to 3 is expansion, 4 to 1 is compression process. And if you look at, take a small look at TS diagram, 1 to 2, Q is added, temperature remain constant, so it is straight line slope. 2 to 3, it is isentropic process in which the entropy remain constant, again it is a straight line slope. 3 to 4, Q is out, temperature remain constant, then it is also a straight line slope. 4 to 1, it is isentropic in which the entropy S remain constant, so it is also a straight line slope. Okay, now there is the actual realization of Carnot cycle. Okay, first start with, we are not going to discuss about Carnot cycle, but just remember the efficiency of Carnot cycle. Nth is I1 minus TL by TH. TL is the second temperature and TH is the initial temperature. TL is the temperature at which the heat is out, and TH is the temperature at which the heat is given to the system. Okay, we again come our the topic which we are going to discuss in the class, gas power cycle. I already discussed why we call it gas power cycle. Working fluid remain gas for the entire cycle, and there are some examples is the spark ignition engines. We know Otto cycles work on spark ignition engines, diesel engines in which compression ignition take place, and gas turbines which depend on the Batron cycles. Batron cycles, we are going to discuss about Batron cycles in depth. Again, there are some assumptions which take place in air standard cycles. The first is air is a working fluid circulated in a closed loop. It is an ideal gas. You know, air is not an ideal gas. Some gases behave ideally at a certain temperature and pressure, but in reality it is a little bit different from its ideal behavior. There are so many assumptions for ideal gas. I'm not going to discuss these assumptions, but for your interest, if you want, let it go. All cycles process are internally reversible. Third one is combustion process replaced by heat addition from external source. It is important to note, combustion process is replaced by heat addition from external source. Why we do it? Because we only take air as a working fluid, and you know heat is added by fuel. We don't study about the behavior of fuel in that mixture or that combustion chamber, so we just assume that heat is added from external source. Fourth is exhaust is replaced by heat rejection process which restore working fluid to initial state. It is also important, just at exhaustion it is replaced ideally by heat rejection process which give our working fluid in its initial condition, which really in realistic way not possible. Air has a constant specific heat value for the room temperature is 25 degree at 25 degree Celsius or 77 Fahrenheit. Okay, we are going to just, we are talking about the assumptions and the terms in next lecture. Thank you for being with us. Have a nice day.